Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 2.5, day 2, entitled Transformations of Functions. And today we're going to talk about these last three objectives. We're going to talk about vertical stretching and shrinking, as well as horizontal stretching and shrinking of a function. And then we're going to talk about the behavior of even and odd functions. Okay, now vertical stretching and shrinking is where you make the graph taller or you make it shorter. So what mathematical operation do you perform on a function to make it more narrow? Now that's narrow visually because you're making the graph taller. You're kind of pulling it up. And hopefully, if you kind of think of a parabola, think of that original function, f of x equals x squared, how would you make that skinnier? How would you make it more narrow? How would you pull all those points up even higher and space them out more? And hopefully you're thinking that you would multiply by a whole number. So you might have f of x equals 4x squared. And then conversely, what mathematical operation do you perform on the function f of x equals x squared in order to make the graph wider? And again, that visually makes the whole graph look wider because you're kind of pushing it down, you're compressing it, you're kind of spreading it out a little bit to make it wider. And hopefully you've realized that you are either going to multiply by a fraction, or you could think of it as dividing by a whole number. Most of the time that's going to be written, though, it's going to be written as a multiplying by a fraction. So you might have f of x equals 1/4 x squared, or you might also see x squared over 4, but most of the time you're going to have the fraction in there out front. So let's take a look at the pictures that the book has for how these graphs get stretched or shrinked vertically. In this first picture, this shows the graph being stretched vertically. Now notice that your endpoints are the same. The blue function is the original one, that's your f of x. And then when you're stretching it vertically, you are multiplying it by a whole number. So you have that value, that c, your constant, out in front. And it just pulls the graph up from its original height, or it pulls it down from its original minimum there. And same thing when you are shrinking the graph, you still have that same endpoint on your x-axis, except now here's the blue original function, and the red function kind of has shrunken down, or it's been pushed down. Same thing over here in your negatives. You're not as low as you were before for the original minimum. Now you've kind of been pushed up a little bit there, so it's being smooshed down. And we call that shrinking when you smoosh it. So let's take a look at these two functions, part A and part B here. And we're still going to use that x squared function like we did in the previous day's notes. So we have f of x equals x squared, and we want to use that function to graph these other functions. So again, I'm going to put that table of values for the x squared function, just as a reminder, because we can use these values to construct our new table of values for these new functions, instead of just having to go to our graphing calculator and type these functions in. Okay, so we want to try and do that. We want to try and use that behavior that we've just talked about to figure out how we would graph this function where we have g of x equals 3x squared. Now again, I'm going to go from -2 to -1, 0, 1, and 2 just to save time. So I'm going to hit those values right there. Just kind of have those other 3 and -3 in there for reference. And if I'm multiplying the whole function by a 3, you have to ask yourself, what is that going to do to my table of values? And what that's really going to do is it's going to make you multiply your y values by 3, or whatever that constant is in front of the x squared. So usually the -2 gives me a 4 when I just have the x squared, but now 4 times 3 will be 12. For the -1, I typically get a 1 out, but now 1 times 3 is 3. 0 is still going to stay 0, and then my pattern repeats. So again, if I graph these, my values might go off a little bit, so I'm going to kind of shift my x-axis down, because if I do it right in the middle, I think I only have a 10 by 10 graph here. So let's do -2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh good, we have just enough room. And then -1, 1, 2, 3, 0, 0. And then I'm going to use my properties of symmetry to help me plot those other 2 points. And now notice that this graph is really, really skinny now. It's gotten narrower. It's been stretched up. It's getting taller. Okay, there's more space in between the vertex and my first points on either side of the vertex. And then there's 3 times as much space between that first point and the second point after my vertex. And then for part B, I'm multiplying by 1/3. So I have x, and then I have h of x. And again, we can go from, actually, let's go from -3 this time. -2, -1, 0, 1, 2, and 3. Because again, here I'm going to either multiply or divide my y values by 3. You could think of it as dividing by 3 or multiplying by 1/3. But for -3, my original value that I get out is 9. But 9 divided by 3 is 3. And then for 2, I typically get, or -2, I usually get a 4 out for the x squared function. But now it's going to be divided by 3, so it's going to be 4/3. And then for -1, I usually get 1. So now that'll be 1/3. 0 still 0. And then I'll get 1/3 and 4/3 and then 3 again. So this is going to be a little bit trickier to graph just because I'm going to have those fractions in there. This is why sometimes it's good to find whole numbers that you can graph that will give you whole number values. Like I could have gone to 6 and -6, or I could have gone to 9 and -9. You could have tried some other numbers besides the -3 and the +3 and find a y value that you know you can divide by 3. All right, so -3, 1, 2, 3, and then -2, and then 1 1/3. So you just kind of have to estimate where that is. And then -1, 1/3, and 0, 0, and then I've got my 1/3, 1 1/3, and then my 3. So again, you can see that this parabola gets really wide, and it's being stretched out. It's kind of tricky because you visually you think that it's getting stretched out along the x-axis, but really you have to think of it as being smooshed on the y-axis because it's a vertical shrinking, so it's being pushed down on the y-axis. So there's not as much space between one y value and the other, between one point and the other. There's a third less space. So it's a little tricky because visually it's getting narrower or wider, but we have to think of it as vertical. It's either being pulled or it's being smushed down. And this is the book graph that has all three of the functions. It has the original one, and then it's got the multiplying by 3, so it makes it narrower, and then the multiplying by 1/3, so it makes it wider. Okay, now horizontal stretching and shrinking. We're going to look at a very different graph for these. Here we have the graph of a sine function. So if you need to take a look at this in your calculator, you can. And if we put this into our graphing calculator, when you graph a sine function, you get a curve. Okay, so it kind of goes like this. Okay, and normally it goes up to 1 and down to -1. It starts at 0, 0. Okay, and it can go back to, it can go along the negative values. But that's what the sine graph looks like. Now, just kind of visualize that and think, okay, if I was going to narrow that graph along the horizontal axis, I would have to be kind of shrinking it. So what mathematical operation would you perform on this original function, the f of x equals sine x, in order to make the graph more narrow on the x-axis? So what would you have to do? And it's, kind of like when we were dealing with the x-axis before and we were trying to move things to the right and to the left. If you wanted to move something to the right, you had to subtract from the x values. Okay, now if you're trying to make something more narrow on the x-axis, you might think you'd want to divide, you'd want to smoosh it all in there, but really you're going to be multiplying by a whole number. And you have to do it to the x value though. So you would have f of x equals the sine of 4x. So you'd have that whole number being multiplied in with the x. And again, you want to inside the parentheses like we had before. And then conversely, what mathematical operation would you do to the function f of x equals sine x in order to make the graph wider, in order to stretch it out? So you'd want to take these ends of this curve and you would just want to pull so that the graph got much, much wider. So you'd kind of have a graph that maybe looked like this. And what we need to do there is we either need to multiply by a fraction, or you can think of it as dividing by a whole number. So we would have f of x equals the sine of 1/4 x. And we will be doing graphs like this later on in the year. We will be dealing with sine and cosine and tangent graphs. So we will be coming back to these concepts. But this is just a good graph to really visualize the movement on the x-axis, the stretching and the shrinking. And the book pictures do a really good job of illustrating this as well. So when you are trying to shrink a graph, you're going to multiply by a whole number. So here's your original graph in the blue on the left, and then your new graph, the f of cx, that's when you're multiplying it by a whole number, and that's the graph in red. Notice that it's really, really skinny now. It's all compressed, it's shrinked. You're covering less space on the x-axis with your graph. And then when you're trying to stretch a graph, you're going to divide by that whole number, or you'd have, they might have like a little, well, they give you the values for c down here. You could also have it 1 over cx. Okay. But again, that red function now, it covers way more distance on that x-axis than what the original blue function did. Okay, so it's kind of opposite. You'd think if you multiply, you'd cover more space, but you actually cover less. And you think if you divide, you'd cover less space, but you actually cover more. So it's, again, that opposite concept on that x-axis to get things to stretch and shrink. Okay, now for example 7 here, we've got this crazy kind of a zigzag function, and I'm just going to plot a couple of points or write down a couple of points for my function here before we go through example A and B. Now we have this function, y equals f of x. We don't really know what it is, but there's a picture of it. And I'm just going to plot down a few points here. Let's see, I've got negative 1, 0. That's the first point on my graph. And then this would be a half. Negative 1 half gets me a 1. And then I'm at 0, 0. And then I'm at 1 half 1. Let me make another little continuation here. I'm at 1 half 1. And then I'm at 1, 0. Okay, so there's some values, just some of the values on this graph. I'm just going from negative 1 to 1. And now we can construct our table of values for these new functions in part A and part B, and then we can graph those new functions as well, because the directions say to sketch the graphs of each of the following functions. So for this first function, for part A, I've got x and I've got y. Now when I'm multiplying in here by a whole number with my x, it's kind of like I'm going to do the opposite in my actual table of values, okay? Because multiplying by that whole number is what's going to make the graph skinnier. So I'm actually going to be dividing my x value by 2 in this case. So instead of starting at negative 1, I'm going to have negative 1 half, 0. Instead of going to negative 1 half, I'm going to go to negative 1 fourth, 1. And we'll still have 0, 0. And then 1 half divided by half, that's a fourth, 1. And then half of 1 is 1 half, 0. So those would be the values that I would graph. And the graphs are on this next slide here. So you could see we had negative 1 half, 0. There's 1 half. Okay, so this is negative 1 half. And I'm at 0. Negative 1 fourth would be right here. I'm up at 1. 0, 0, 1 fourth, 1 half. Okay, so those are the values that we had in our table of values. So you can see that the graph gets much skinnier. It's much compressed. You have a lot more of the zigzags in the same amount of space. Or you could think of it as taking less space to get one of those little zigzags. Okay, and then for part B, I'm going to do the same thing. I'm going to think, okay, now what would I have to do to my original table of values, this blue table of values up here? What would I have to do to that in order to adjust or accommodate for the 1 half x in my new function? Now again, when we're dealing with horizontal axes, the stretching and the shrinking, we're kind of doing the opposite of what is actually present in the function. So I have this 1 half in my function, but really what I want to do is I want to multiply by 2. So I'm going to take all my x values, multiply by 2 to the x values. So when I make my table of values, I'm not going to start at negative 1. I'm going to multiply that by 2, and I'm going to start at negative 2. And then at negative 1 half times 2 would be negative 1. 0 still 0. 1 half times 2 is 1. And then 1 times 2 would be 2. And then I would still get the same values out. 0, 1, 0, 1, 0. And again, that graph is going to be shown here. Okay, my first value was, oh, it doesn't actually show up here. That would be down here. It would be negative 2 would be down here. Okay, and then, oh, wait, no. Negative 2 would be right there. Okay, good. I was thinking they had the halves on the graph, but they don't. Good, they have it. Okay, so here's my negative 2 value. So I'm at negative 2, 0. Negative 1, I go up to 1. 0, 0, 1, 1, 2, 0. So there are my table of values that are shown in the graph. And again, we're stretching out how long it takes us to do a couple of those little zigzags on the x-axis. So instead of that original zigzag going from -1 to 1, now it's going from -2 to +2. Okay, and just like in part A, instead of going from -1 to 1, I went from -1/2 to +1/2. So I'm either shrinking it by 2 or I'm multiplying it by 2. So you can see very clearly now in the function, okay, I was multiplying by 2, but really I shrunk my space by half. Here I was multiplying by a half, but I actually expanded my space and went from -2 to +2. So seeing the function and the graph and having those table of values, I think really makes a clear connection here as to how you have to do the opposite on the x-axis. You're doing the opposite operation to get the visual effect that you want. Okay, last concept is for even and odd functions, and this should be something that you have talked about before. In Algebra 2, you've talked about even and odd functions. Even functions basically have an even power. Like here, they have x squared. And what happens is when you plug a value in for an even function, if you plug in a positive value or a negative value, you get the same thing out. So if I put in a -2 to this function, I'm going to get a +4 out. If I put in a +2 to this function, I'm going to get the same thing, +4 out. So an even function is following this rule that f of -x equals f of x. That means you get the same value out whether you put in that negative value or that positive value for x, you get the same y value out. And even functions are going to have symmetry around the y-axis, always, just like parabolas. Now, odd functions are functions that have odd exponents. So here we have x to the third, or it could be x to the fifth, x to the seventh, x to the ninth. And what happens then is that when you plug a number in, f of -x, into the function, you actually get negative f of x out. So if I plugged in a -1 to x to the third, like they have here, if I plugged in a -1 and then I cubed it, negative times negative is a positive, times a negative gets me a -1. So when I put in -1 to the function, I get a -1 out. Okay, so that's the rule that odd functions are following. So knowing those concepts can help us further understand behavior of graphs and functions. And this is the chart that your book has that explains this rule. It's got the rules right here very neatly. And it does a good job of showing us the symmetry as well. The even functions have to have symmetry on the y-axis, and then the odd functions have to have symmetry around the origin. Okay, so there's not going to be any symmetry around the x-axis here. But what we're going to do is we're going to test for even and odd functions. And basically how we can do this, how we can determine if a function is even or odd or neither, is that we plug in a negative value for x. So I'm going to take this original function. Originally I have f of x equals x to the fifth plus x. And we want to figure out if this is going to have an even or an odd behavior for a graph or neither of them. So I'm going to replace the x with a negative x. So I'll have negative x to the fifth plus negative x. And then I'm going to simplify it, and I'm going to see if I get my original equation back again or not. And here if I had negative x to the fifth, that would get me negative x to the fifth minus x. Now, you might say, oh, that's not the same as my original function. But both of these terms are negative. So I can take out that -1 like a GCF, and then I do get part of my original function back, except it's been multiplied by a -1. So I have this x to the fifth plus x, I have that, but now I'm multiplying it by a negative 1. And that is the characteristic for an odd function. When you have f of negative x equals negative f of x, that's the behavior for an odd function. For part B, I have g of x equals 1 minus x to the fourth. So I'm just going to substitute in a negative for the x. So I'll have 1 minus negative 1. Oh, I'm sorry, negative x to the fourth. And negative x to the fourth, it's going to be 1 minus x to the fourth. And that is actually the same as my original function, because when I take a negative x to the fourth power, I end up getting just a positive value. So since I have the exact same thing back again, that's like plugging in a negative. F of negative x is equal to f of x. So that's going to be even. Okay, and for our last example here, part C, we're still going to test this the same way. I'm going to plug in a negative x for the x. So I'll have 2 times negative x minus negative x squared. So 2 times negative x, that would be a negative 2x. And then negative x squared is going to be a positive x squared. But I still have that minus there, so it'll be minus x squared. And I almost have my original function back again, except I have that negative out in front of the 2. And even if I took a negative out, like a negative 1, I'd have 2x plus x squared. Oop, x squared. So that's still not my original function. So this is going to be a neither scenario. That function's not going to be even or odd. It's just a function. And here the book has graphed those so that you can visually see how our first one was odd. Any odd graph is going to have this kind of a little hump or a little bump in the middle of the graph. Our second one was even, so that's going to be kind of like a parabola. And then this last one, it's just neither. So when you're testing for even and odd behavior, you just want to substitute in a negative x for the x and simplify the expression and see which of those behaviors you get. So here's your set of practice problems that you can work on these concepts. And if you have any questions, come on in and see me before school.